From this transaction data, we need to predict if a transaction is fraudulent or genuine. If a customer complains for a fraudulent transaction to the bank must pay back the money. And this way, if there are a lot of fraudulent transactions happening under a bank, its security systems are not that solid. So the bank will lose huge amount of money every economic year. So, of course, a machine learning system could be thought of that could, alarm or detect such false transactions or fraudulent transactions. But every week in a country like a populated country like India, every week the number of transactions happening was of the order of 30 or 40 millions. Okay, so let's say 30 million transactions happening in 1 week. Out of the 30 million transactions, how many fraudulent transactions are there? 5,000 or less. So compare the size of the two classes. 30 million total, 5,000 or less in the fraudulent class. So huge number of transactions are actually genuine. Otherwise, the economy would just collapse. So this situation happens in many other cases also. Cancer classification, you randomly scan the, let's say, CT images or X-ray images from 1,000 patients, maybe 4 or 5 of them will show signs of development of internal tumors or lesions that are indicative of cancer. Even if it is 4, and these 4 patients are completely misclassified by your classifier, they are stamped as benign, like the other 96. So what is the accuracy of your classifier? It is 96%, because for 96 people, the classifiers predicted the right category. For 4 people, it predicted wrong, but it was designed to capture only those 4 people who have signs of cancer and who should immediately be under treatment. Am I clear? So this way, the target class is just simply missed. Although your classifier is very nice at classification accuracy, its use is actually negative, 0. That's where the class imbalance problem comes. So as I said, one class which is very important, or which is said to be the target class, that target class is of the size of this mouse, and the other class is of the size of this elephant. And that's how they are doing a great mismatch. Even now, examples from the majority class, the bigger class, are usually well classified, and the examples from the minority class are misclassified. Under that condition, if the minority class is not biased properly, for example, these are the 2 classes. These are these red ellipse gives you the portion of the data space from where the majority class points can come. All points can be sampled from this red ellipse, that is the geometric distribution of points from the blue class, and the blue ellipse shows you the geometric distribution of points from the red class. Now the problem is, if in your training data only few examples come from the red class, okay, which are stipulated, confined to a very small region, this dotted green line is your ideal decision boundary between the 2 classes, because it has minimum Bayesian risk, a statistical quantity which actually tells you how good your classifier is statistically. But if you provide this data to a support vector machine or similar classifier, it will end up with this solid green line. And now the classifier looks at it like, if a point comes from the left of the solid green line, it is in the red class. If it comes from the right of the solid green line, it is in the blue class. Now, if you're during the test phase, if such unseen points are coming, if these are your test points, all such points will be misclassified. Okay, so biased training data, which is very often the case because sampling systems do not work properly, biased training data coupled with class imbalance will actually make all regular classifiers to fail. And class imbalance comes in various situations like credit card fraud detection, machine anomaly detection, then this any kind of medical disease-based diagnostics where disease, fraud, anomaly, all these are rare events forming the minority class. Okay. So as I said, unbiased versus biased data sampling. Biased data sampling also, that is basically like adding insult to injury. You are not adequately spreading all your data items over the entire parameter space. That's going to make your life even very, very poor. Okay. So there are some slides about the confusion matrix, and I know all of you are very good at confusion matrices. So confusion matrix is actually like this. For a two-class classification problem, we can find out quantities like accuracy, recall, precision, F1 score. These are just textbook figures of merit for judging the performance of a classifier, but they are not adequate if there is class imbalance. In case of class imbalance situation, the accuracy may be shown to be very high actually when it is very less. So thereby comes the G mean index. In this particular paper, which is published, I think, in 2021, although accepted in 2020, this on the choice of appropriate performance indices for imbalance class data classification, we show that indices like G mean, which is basically a geometric mean of sensitivity and specificity, or true positive rate times true negative R, that actually is very good. For if this situation happens, that all the negative examples are predicted as negative, but actually which are positive. So that means the misclassification for these four, the G mean index will become 0. If these four are properly classified, these four are those cancerous samples or the target class. If these are properly classified, then the G mean will be, 1. So instead of using regular figures of merit, we should switch to this sort of things. There are a few different algorithmic approaches for class imbalance handling. The most popular techniques are data rebalancing, oversampling, generate artificial data items inside the majority class so that the majority class, generate artificial samples inside the minority class, so that the minority class may appear to be sizable, may appear to have a large size, and the classifier decision boundary may not get biased towards the majority class. So oversampling, generate artificial samples in the minority class. Undersampling, eliminate or delete extra points from the majority class so that the majority class gets down to the size of the minority class. Then there are cost-sensitive methods which try to modulate the cost function of the classifier so that misclassifying a point from the minority class may be very heavily, penalized compared to misclassification of a point from the majority class. Then there are algorithm level approaches like kernel modification methods, active learning, and so on, or combination of these two. So this is the idea of undersampling and oversampling. In undersampling, you are deleting points from the majority class. In oversampling, you are creating artificial points in the minority class. One such very interesting oversampling technique was SMOT, which stands for synthetic minority oversampling technique. And in SMOT, what we do is, this is our minority class, this is the majority class. So we select any one minority point like this, then we select a number of its nearest neighbors here, which is 3. So we select 3 of its nearest neighbors, and then we randomly pick up a point from among the nearest neighbors and create a new point on the line joining this point and that point, the target point, by this convex combination. So this is the new synthetic sample. So we can do it multiple times for different target points to generate different samples within the minority class. But then there are a lot of problems. Usually the classifier starts failing for the regions where there is an overlap for points from the two classes. So there are a lot of, advances or improvements over the SMOT approach, one of which is the stomach link. So what we do is we first populate the minority class with SMOT, then we identify such closest pairs in which one element is from the majority class and the other element is from minority class. Such couples are called tomic links. And then we delete all the tomic links. That actually separates the two classes very well. And such class separation helps the machine learning algorithm to put a right decision boundary. Okay. Similarly, we have random undersampling. We can undersample by looking at the nearest neighbors of each of the points from the majority class. If a majority class point has lot of, lot of the nearest neighbors from the minority class, like these 3 points, they should be deleted at first. That is undersampling under edited nearest neighbor. Similarly, we can. This is one of our first approaches where we attacked where we tackled this problem of class imbalance in support vector machines by modifying the regular support vector machine cost function with 2 additional terms, which actually provide unequal penalties for classification, for misclassification on the minority and from the majority class samples. This paper and its full codes are available in here. So I actually don't have enough time to explain it. So I will gradually now conclude because I think the time is really limited. This one, the k-nearest neighbor classifier, we all know this is one of the simplest classifier. This example just shows how we can modify it to handle class imbalance. So in k-nearest neighbor, we have training point from both the classes, and when a new test point comes here, we check to which class its nearest neighbors are belonging. Most of the nearest neighbors are belonging, and we invert the same class for this new test point. So k-nearest neighbor goes by very simple rule. A person is identified by the company that he or she keeps. If all your friends are very sober and genuine, you are also very good. Otherwise, there is a problem. So in a multi-class class imbalance scenario, we propose a very simple weighting scheme which could actually, equip k-nearest neighbor with the class imbalance handling mechanism. For all classes, the idea, if there are, let's say, 3 classes, the ideal probability of getting a point from these classes are 1/3 each. So for C classes, it is 1 upon C. The original probability, PC, is number of points from that class in the training set divided by the total number of points, which is MC by N. Now, R and PC should be equal if all classes have same number of points. So 100 points, 50 from class A, 50 from class B. What are the actual probabilities? 50 by 100, which is actually half. If they're not same, we calculate these class-specific weights, WC, which is R by PC. Now, what we do is, here there are 20 points total, 4 from blue class, 16 from the red class. Therefore, the ideal probability of the 2 classes are half and half, 0.5 and 0.5. The actual probabilities are 4 by 20, which is 0.2, and 16 by 20, which is 0.8. Now we compute the weights by dividing R with P for the 2 classes, which is 0.5 by 0.2, that gives us 2.5, and 0.5 by 0.8, that gives us 0.625. Now, when a new query point appears, this case, look at this case, when this new point appears, we have 1 neighbor from blue class and 2 neighbors from the red class. This 1 and 2 in regular KNN would predict this point to belong to the red class. But here we are revising these counts by multiplying this 2 with this weight and this 1 with this weight. So in this version of KNN, we are actually modifying the counts of neighbors from different classes by multiplying them with these weights. And when we multiply, we see the revised count of neighbors from blue class is more. So in this revised KNN, this point will actually be stamped or tagged to belong to the blue class. This is called global imbalance handling scheme, and our paper actually, this one in IEEE TNNLS, this actually examines this scheme in greater details with a lot of experimental results and so on. Class imbalance is very much there in deep learning era as well, especially in many image data sets where we have such a long-tailed distribution of the images. Some images appear very less number of times compared to many other images which appear high number of times, or similar images. SAM 397 is a benchmark data set for multi-class class imbalance handling. And in this particular work, which was done in, which was published in the ICCB 2019 conference, we came up with a GAN-based oversampling technique. GAN, I don't know how many of you have heard this term. You should have heard this term at this particular era if you were doing some research in machine learning. This is one of the major breakthroughs in deep generative models. Generative adversarial networks, they are famous for generating artificial images, synthetic text, then artificial speech signal, whatnot. If they are shown adequate examples of some particular data item, they can give rise to such data items artificially.